Hello students. So today we are going to do some questions related to relations and functions. The questions which were there in the previous CBSE board papers are most likely questions. Okay. So in the relations and functions, most important is proving equivalence relation. Okay. Relation is defined and you have to prove it to be equivalence relation. This type of question can be asked for 3 or 4 marks. Okay. So in this you have to prove it to be reflexive, then symmetric and transitive. Okay. Then another question which can be asked for 3 or 4 marks is from on one and on two functions, that is proving a function to be bijective. Okay. One is the function has only one image. Okay, this is one. And onto is all the elements in the codomain. Okay, are mapped to the elements in domain. That is, range becomes equal to codomain. Then we say the function is onto. Right. So this is injective. This is surjective. If both are happening at once, then they are called. The function is called bijective. Okay. And yeah, these two things are mostly asked in the question paper. Okay, and some questions are also based on this assertion, reasoning. Then case study based questions are also asked from this chapter. Okay, so let's start with some questions. So this is a question: show that relation R, set of all a comma b such that a minus b is divisible by 3 and a comma b belongs to natural numbers. Okay, is an equivalence relation. So you might have solved this kind of questions earlier also, but here the way you write the solution, that is how you write the steps, okay, that is more important because marks are given based on that. Okay, so let's start with the proof, that is how to solve it. So starting with the solution, first you have to prove it to be reflexive. Okay. So to prove reflexive, you have to take one element from set of natural numbers, say for any a belonging to set of natural numbers. Okay. I'm taking one element in the form a comma b from R, right? So we can write this as a minus a is divisible by 3, correct? A minus a is 0. So you can write here a minus a is 0, which is divisible by 3. This implies our element a comma a belongs to relation set. Okay. So we can say that R is reflexive. This is true, right? Because a minus a is 0, 0 is divisible by 3. And by definition, we have proved that this element belongs to set of the relation set. Okay. Secondly, you have to prove for symmetric. Okay. For symmetric, you have to take one element, let's say a comma b belonging to R. That is, we are taking one element from relation set. Okay. According to definition, we will get a minus b is divisible by 3. Correct? This implies if I take minus outside, this will be b minus a. This is for all a comma b belonging to set of natural numbers. Okay, divisible by 3. This is true, right? If you take any number here, you can write this. Okay. So this implies minus of b minus a divisible by 3. So we can write b minus a is divisible by 3. Okay. This implies b comma a belongs to R. Okay, which is a relation set. Okay. So we have proved that if a comma b belongs to R, then b comma a also belongs to R. So it makes R symmetric. Okay. Now we'll prove for transitive. So again you have to choose two elements, that is let a comma b belongs to R and b comma c belongs to R. Okay. So according to definition, a minus b is divisible by 3 and b minus c is divisible by 3. So we can write here a minus b plus b minus c is divisible by 3. Okay. So this implies minus b and plus b. So this will get a minus c is divisible by 3. So this is by definition we can say that a comma c belongs to relation set. This implies R is transitive. Okay. Okay, let's solve this. So let L be the set of all people in locality. Okay, R be defined as a set of all x comma y belonging to R. Okay, if and only if x and y are like-minded. Okay, this is the condition which is given. Now we have to prove that R is equivalence relation. Okay, so starting with our reflexive. Okay, so first this is L with the set of all people in locality. So x and y are like-minded people. Okay, so I'm taking x for any belonging to L. Okay, so this implies x is you have to take x comma x, right? This implies both are like-minded. Both the persons are same, so both are like-minded. Okay, so this is true. Reflexive is true. Then for symmetric. Okay, so for symmetric, mm, I'm taking, let's say, x comma y belongs to R. Okay, or x and y for x and y belonging to L. Okay. So according to definition, x and y are like-minded. So other way also it is true. That is y and x are like-minded. Okay, this implies y comma x belongs to R. That is relation set. Okay, this implies this set R is symmetric. Okay, now we have to prove for transitive. So let's say x comma y belongs to R and y comma z belongs to R. So according to definition, x and y like-minded and y and z like-minded. Okay. So this implies if x and y is like-minded and y and z like-minded, then we can directly say that x and z are like-minded. Correct? This implies x comma z belongs to R. So it is transitive. So it is R is an equivalence relation. Okay. Here one more thing I would like to add, that is here you have to write after this for x, y, z belonging to L, that is from which set they are. Okay, and for reflexive, okay, you can directly take element from say your relation set. Okay, so you can directly write that x and x are like-minded. Okay, so you can directly start with an element from relation set. Okay. Next question, show that R is defined, that is a relation set is defined A comma B, set of all A comma B such that mod of A minus B is a multiple of 4. Okay, and it is defined on a set A, which is a set of all integers, and this integer is from 0 to 12. That is all the elements belonging to integers, that is 0, 1, 2. So I'll write here A set 0, 1, 2 till 12. Okay. So this we have to prove that it is an equivalence relation, and also you have to find all the elements related to 1. Okay. So first thing, starting with the reflexive. So you can directly take an element from a relation set. Say let A comma A belongs to relation set for all A belonging to this set. Okay. So here we can directly write, right? According to definition, mod of A minus A is a multiple of 4. Okay. This is 0, right? So 0 is a multiple of 4. Okay. So we can say that R is reflexive as we have proved the condition. Next is we have to prove it for symmetric. So for symmetric, you have to take one element, say let A comma B belonging to R for all A and B belonging to set A. Okay. So according to definition, this A minus B is a multiple of 4. Okay. So this we can write minus of B minus A is a multiple of 4. This is the same thing we have done for divisible. Okay, divisible by 3 we have taken. This is for multiple. So same type of steps you have to follow. So here we can write B minus A is a multiple of 4. Okay, this there is a mod sign here, right? So we are taking that minus 1 outside. So b minus a is a multiple of 4, which implies b comma a belongs to R. Okay. So we can say that R is symmetric. Okay. Next is transitive. Okay. So let a comma b belongs to R and b comma c belongs to R. Okay. Two elements we have to take from R, and you have to write for all a, b and c belonging to set A. Okay. So this implies mod of a minus b is a multiple of 4 and mod of b minus c is a multiple of 4. Okay. So we can write this as a minus b plus b minus c. Okay. Which is our a minus c is a multiple of 4. Okay. You can write here mod sign also. So this implies a comma c belongs to R. This implies R is transitive. So we have taken same steps as we had done for the divisible. Okay. So this is transitive. So R is an equivalence relation. Now there is one more sub question, that is you have to find all the elements related to 1. So to find this you have to write your relation set. Okay. So you have to take each element, say 0, or you can start from 1 also. With 1 you can take. Okay. Related to A. So here you have domain and codomain, right? And both the sets have same elements, that is 0 to 12. You have to just find the elements which are related to 1. Okay. So your B is fixed. So you have to fix your B and you have to change only A. Okay, so you have to start from 0. So see 0 minus 1, which is 1 minus 1. Okay, 1. It is not a multiple of 4. So this is not there. 0 we can't take. Take 1. 1 minus 1. 0. It is a multiple of 4. So we can take that. So 1 comma 1. Okay. This one element we can take. I'll just write the elements. Okay. Then 2 comma 1. 2 minus 1, which is 1. It is not a multiple of 4. Then take 3. 3 minus 1, 2. No. For 4. 4 minus 1, 3. No. 5 minus 1. Yes. So you can take 5 comma 1. Okay. Then 6. 6 minus 1, 5. 7. 7 minus 1, 6. 8 minus 1, 7. Then 9 minus 1. So 9 you can take. Okay. 9. 9 comma 1. Okay. Then next element is our, this is 0. 4 ones are 4. 4 twos are 8. Then 4 threes are 12. Here only 12 element. 12 element is there. So 12 minus 1 is 11. Okay. if it was 13, 13 minus 1 is 12. Okay, so up to 12 is there. So these are the elements which are there in the relation set which are related to 1. So we have a set 1, 5, 9. These are the elements which are related to 1. Okay, keep in mind related means this element is from your codomain set. Okay,